This section explains what statistical mechanics is and the single move at its heart. A block of ice has too many atoms to solve, yet it melts at one temperature sharply. Statistical mechanics explains the simple behavior of complex systems, and the whole trick is a refusal. Stop tracking the single system. Track the ensemble of all similarly prepared systems instead. Any one random walk is unpredictable. The distribution over all walks obeys clean laws. The move is deliberately giving up on the instance to win the aggregate, because averaging is where the microscopic mess cancels, and simple macroscopic quantities, temperature, entropy, pressure, emerge. Everything downstream, ensembles, entropy, phases, fluctuations, is this same substitution applied again. Here is the surprise. Intractability at the part becomes lawfulness at the whole, precisely by not solving the part. This section explains why statistical mechanics begins by refusing to ask about the single particle. Complexity dissolves the moment you stop asking about the individual. Any single random walk is irregular, its trajectory hopeless to predict. But the ensemble of all such walks obeys elegant, exact law, its endpoints spread into a clean Gaussian. That inversion is the whole discipline in one move. You replace the intractable one with the tractable many, and the collective quantities you actually measure, temperature, entropy, pressure, emerge as properties of the collection, never the atom. Setna's chapter is the promissory note the book redeems. Every later concept, entropy, phases, critical points, Monte Carlo, is this same trade, complexity below buying simplicity above. The particle is noise. The distribution is signal. This section explains why the random walk is the cheapest instance of statistical mechanics and what survives when you add many independent steps together. Add enough independent small steps, and everything about the individual step forgets itself except its mean and its variance. What survives is a Gaussian, spreading as the square root of n. Setna opens the book here because the random walk is the cheapest instance of his whole thesis. The drunkard, the polymer coil, the diffusing dye, the stock price all obey one macroscopic law, indifferent to their microscopic rules. That indifference is emergence. The continuum limit, the diffusion equation, is a fixed point that the summation flows to, washing out the substrate. The generative move to keep is this: coarse grain, a sum of many independent parts, then ask what few numbers refuse to be forgotten. Statistical mechanics is this move performed at Avogadro's scale. This section explains why the random walk is the minimal system where complexity below gives way to simplicity above. Some enough independent fluctuating steps, and the microscopic identity of each step stops mattering. What survives is a single scaling law. Whatever a coin flip, a perfume molecule's collision, or a polymer link contributes, the root mean square displacement grows as the square root of n. The step distribution sets only the prefactor. That indifference to detail is universality, and it is why the macroscopic world admits simple mathematical law at all. Gravitation emerges from virtual gravitons, the way the diffusion equation emerges from long random walks. The chapter's work in the book is to make that emergence concrete and cheap. The random walk is the minimal system where complex below, simple above becomes a provable square root of n, not a slogan. Everything downstream is this move, iterated. This section explains why equilibrium is honestly described by an ensemble rather than a single trajectory, and how one volume count generates all of thermodynamics. Chaos is the eraser. A many-body trajectory scrambles every knowable detail except the conserved energy. So once that scrambling is done, what remains to describe equilibrium is a uniform measure over all states sharing that energy, uniform measure over all states sharing that energy. The whole move of the chapter is that one scalar, omega of E, the phase space volume of the energy shell, generates thermodynamics as its derivatives. Temperature is how fast omega grows with energy. Two coupled systems settle where total omega is maximal, which is precisely where that growth rate matches. That matching is equal temperature, and heat flow is entropy maximization. Entropy is the logarithm of omega. From this, you can already predict every case, because each thermodynamic quantity is a derivative of one volume count. This section explains why the statistical description of many particles begins by abandoning the trajectory. Give up on the trajectory. That surrender is the whole method. Newton's equations for n atoms are unsolvable. There are too many particles, and chaos scrambles any error exponentially, so the exact path is both intractable and useless. The chapter's move is to convert that defeat into a definition. The dynamics smears every isolated system uniformly across its constant energy surface in phase space, so you replace time following with a flat average over that surface. That average is the microcanonical ensemble. Equilibrium becomes geometry rather than motion. Temperature, pressure, and entropy then fall out of one quantity, the volume of accessible phase space. The primitive to carry forward is this. When a temporal problem is hopeless, count states instead of tracking them. This section explains why equal weighting over the energy surface is a theorem, not an assumption you have to apologize for. Equal weighting over the energy surface stops being a confession of ignorance and becomes a provable result. That is what this chapter is for. Two conditions do the lifting. The first is Liouville. Hamiltonian flow is incompressible, conserving phase, space volume, so trajectories only stir the surface, they never re-weight it. The second is ergodicity. The stirring is thorough enough that one trajectory eventually samples the whole surface. Together, these two conditions collapse a single system's long-time average onto the microcanonical average over all states. The equilibrium you actually measure equals the ensemble you merely postulated. The boundary that reveals the structure is this. Incompressibility alone will not suffice. Stirring without genuine mixing, as in integrable systems, leaves the time average dependent on which trajectory you started from, and the identity breaks. This section explains how the microcanonical ensemble stops being a bookkeeping assumption and becomes a theorem. Until now, the ensemble was an alibi for ignorance. It knew only that energy is conserved, so it averaged democratically over the whole energy surface. This chapter converts that alibi into a theorem. In two moves. The first move is Liouville. The Hamiltonian flow is incompressible. Phase space volume is conserved, so trajectories merely stir the energy surface and never concentrate onto an attractor, which fixes the relative weights forever. The second move is ergodicity. A single trajectory eventually smears across the entire surface, so its time average collapses onto the surface. Average. Together, Liouville and ergodicity license equal weighting as what the dynamics actually does, rather than what we assume. Here is the inversion that carries the whole chapter. Equilibration here is a lone orbit densely filling its energy shell. It is not a decay onto an attractor, because Liouville forbids attractors outright. This section explains why entropy is one number wearing three names. Three vocabularies: the engine builder's irreversibility, the chemist's disorder, the information theorist's ignorance, all name a single scalar. Entropy. S equals Boltzmann's constant Kb times the logarithm of omega, the log count of microstates compatible with what you know. The chapter's whole move is triangulation, fix the number, rotate the light. Carnot's unrecoverable work, a mixing that will not spontaneously unmix, a message you cannot compress further. Each of these measures the same missing information. So, a bound proved in one dialect binds all three. That identity is the payload, not the three readings themselves. The heat death of the universe and Shannon's channel limit are the same statement read at different scales. Entropy is three questions, whose single answer is the count. This section explains entropy as one scalar read in three currencies. Entropy counts the microscopic states compatible with what you know of a system macroscopically. That single count is Carnot's engine shedding usable work, a gas mixing into uniformity, and your ignorance of which microstate actually holds. These are one quantity, the logarithm of a count, seen from three sides rather than three separate quantities that merely resemble each other. The generative move is this. Fix a macroscopic constraint, count the compatible microstates, take the logarithm. Irreversibility is that count growing. Disorder. Is it being large? And ignorance is it being what you have not pinned down? Once entropy is the state count, every later face, Shannon's bits, a black hole's area, is the same logarithm wearing different units. This section explains the 6 free energies as one trick applied 6 times. A free energy is what remains once you integrate out the degrees of freedom you refuse to track, the bath, the reservoir, the microstates. What is left is an effective energy whose minima fix equilibrium for the variables you kept. The 6 differ only in which exchange you open. Energy with a heat bath, volume against a piston, particles through a permeable wall. Each open channel trades a held variable for its conjugate, and the Legendre transform is the bookkeeping. So the 6 are just the combinatorics of which conjugate pairs you let float. Predict the 7th yourself. Name a new exchange, swap the pair, subtract the product. Nothing else is going on. This section explains what every free energy has in common. Each one is the same refusal. You decline to track part of a system. You sum over everything you agreed not to watch, and you take the logarithm of what survives. That survivor is a new, effective energy for the parts you kept. Ignore a heat bath, and the Helmholtz free energy is what remains, energy minus temperature times entropy. Ignore particle exchange, ignore fast internal motions, ignore spatial detail. Each choice of what to integrate out yields its own ensemble and its own free energy. The chapter's one move is this, partial trace over the unwatched. Its payoff is that reasoning about the remainder is easier and more comprehensible than tracking the whole. This section explains why quantum statistical mechanics falls out of a single move, counting how many identical particles occupy each mode rather than which particle sits where. Strip the labels of identical particles and the whole subject follows. Classically, you count configurations by asking which particle sits in which state. Quantum mechanically, the particles have no names, so the only fact is how many occupy each mode. Exchange symmetry fixes the occupancy ceiling. Antisymmetric wave functions forbid two fermions in one mode, 0 or 1, while symmetric ones let bosons pile up without bound. Fermi, Dirac, and Bose. Einstein are just those two ceilings. Planck radiation, the Fermi sea, condensation, every result in the chapter is one consequence of counting occupation numbers instead of trajectories. The classical gas is only the dilute limit, modes so sparsely filled that the ceiling never binds. This section explains why quantum statistical mechanics is not a second theory, but the classical ensemble with two substitutions. The phase space distribution, rho of P and Q, cannot survive the uncertainty principle, so the density matrix replaces it. Distinguishable counting cannot survive identical particles, so exchange symmetry replaces it. The whole arc of the chapter runs from abstract to concrete through simplifications. From that operator, rho, drop the interactions, and the intractable many-body problem collapses to one question: how do single-particle eigenstates fill? Bose or Fermi is merely whether swapping two particles costs a sign. That single filling rule is what the chapter is for. It generates black body radiation, Bose condensation, and the metal alike. Exotic phenomena. One primitive. This section explains how physics forces answers out of a model it cannot solve in closed form. Most statistical mechanical systems have no closed form, no tidy partition function, entropy, or free energy. So the chapter is a fork. Two ways to force answers out of an unsolvable model. The first way is to sample it. You build a Markov chain whose stationary distribution is the Boltzmann weight, so that wandering for long enough averages to the ensemble. Monte Carlo on the Ising model is the canonical case. The second way is to expand it, perturbing around a limit you already solve. Here is the surprise that carries the chapter. The perturbation series fails near a phase transition, and the place where it fails, its radius of convergence, is exactly the phase boundary. Where the expansion breaks, a new phase begins. Analytic failure is the physics announcing itself. This section explains what to do when the partition function refuses to integrate, which is the generic case. You stop trying to solve it, and instead you either sample or expand. Sampling means you build a Markov chain whose stationary distribution is the Boltzmann distribution, run it, and read equilibrium averages straight off the trajectory. This is Monte Carlo, anchored on the Ising model. Expanding means you start from a solvable limit, either zero temperature or infinite temperature, and add small terms. This is perturbation theory. Here is the chapter's understated surprise. Whether that series converges is the very question of whether you sit inside a phase. A phase boundary is precisely where the analytic continuation breaks. So, computation does real work here rather than merely patching hard integrals. The failure mode of one method diagnoses the physics, and the phase structure is exactly what the other method must simulate. This section explains order parameters, broken symmetry, and topology. Throw away the Hamiltonian and keep only which ground state the system locally chose. When a continuous symmetry breaks, each point must pick one degenerate vacuum. That choice is the order parameter, a field valued in the space of broken symmetry states. The move of the chapter is this. Every emergent property, the rigidity, the defects, the low-energy excitations, follows from the geometry and topology of that space alone, and not from the microscopics. A magnet spins live on a sphere, and a crystal's phase lives on a torus. The holes in those spaces are the defects themselves, classified by homotopy. Sedna's compression is that what you measure macroscopically is a property of the broken symmetry, not of the material. Name the residual space, and the next case predicts itself. This section explains how a phase of matter follows from the symmetry it broke and from nothing else. Forget what a phase is made of. Ask only which symmetry it broke. That single choice fixes an order parameter space, the manifold of equivalent broken ground states. From its shape alone, everything else follows deductively. The slow excitations are its gentle twists. The defects are the knots. Topology forbids you to comb out. Sedna's chapter is one 4-step algorithm. Identify the broken symmetry, name the order parameter, examine the excitations, classify the defects. The claim underneath is that emergent physics is bookkeeping on a quotient space, accounting run on the space of broken states rather than on a Hamiltonian. The water versus ice reversal carries the point. The disordered phase is the more symmetric one because a phase is the ensemble rather than the snapshot. This part explains why the way a system settles its own noise is the same as the way it answers a push. A system in equilibrium cannot tell a spontaneous fluctuation from your deliberate nudge, so the way it relaxes a fluctuation back to zero is the way it responds to a small external force. That equality is the fluctuation dissipation theorem, the chapter's single primitive. Correlation, response, and dissipation are one object read 3 ways. The correlation function tracks how a fluctuation here and now echoes there and later. The susceptibility measures the driven response. The dissipation, the energy bled to heat, is that response's out-of-phase part. Equilibrium noise therefore predicts non-equilibrium behavior. Measure how a thing jiggles on its own, and you already know how it will answer when pushed, and how much it will warm. This section explains the fluctuation dissipation theorem, the claim that a system's spontaneous wiggling and its response to a push are one and the same measurement. Kick an equilibrium system and watch it yield and dissipate. Leave it alone and watch it wiggle. These are the same measurement. That is the whole chapter. A system's spontaneous thermal fluctuations already encode its response to any gentle push because one microscopic dynamics generates both. Correlation functions quantify the wiggling, and susceptibility quantifies the yielding and dissipating, and the fluctuation dissipation theorem states that they are one object. Reactive response and dissipation are the real and imaginary parts of a single complex susceptibility. Causality alone, the fact that a response cannot precede its cause, locks that a response cannot precede its cause, locks those two parts together. You never need to disturb equilibrium to learn how it answers a kick. Its own noise has already told you.